China didn't just build stadiums for the future, it built stadiums that make the present look embarrassing. While the United States is getting ready to host the 2026 World Cup in Beijing, multi-purpose bowls that were never designed for football, China has been quietly constructing venues with retractable roofs on magnetic levitation tracks, facades that literally clean the air, and passive cooling systems that use zero electricity. One of these stadiums was built from the ground up in 34 months. You heard that right. The entire steel skeleton, the roof, the pitch, the seats, done in under 3 years, while the average American stadium renovation takes longer just to clear environmental review. What you're about to see isn't just architecture, it's a statement. And it starts with the most ambitious football complex ever attempted, a project so massive it didn't just build a stadium, it built an entire football universe. You don't build a football park, you don't build a football campus. Guangzhou Football Park is a football universe, 50 full-sized pitches, one main stadium holding 100,000 seats, and an AI-managed turf rotation system that treats grass the way a Formula One team treats tires. Every single pitch is monitored, rotated, and replaced on an algorithmic schedule, so the surface is always at peak condition. The main arena alone covers a footprint so massive it would swallow most American stadiums whole. But here's where the engineering gets insane. The stadium wasn't just designed to host matches, it was designed to sustain football at an industrial scale. The infrastructure beneath those 50 pitches runs a buried network of drainage, irrigation, and climate sensors that feed data back to a central AI system around the clock. Nothing is left to chance. Nothing is left to a groundskeeper with a hose. Then, the entire project collapsed. Evergrande, the company that commissioned it, imploded in one of the largest corporate failures in modern history. Construction froze. The cranes stopped. And yet the structure was so far along, so deeply engineered, that it couldn't just be abandoned. It was finished anyway. A stadium that survived the financial death of its own creator. That's what happens when engineering is built to outlast everything, even the people who paid for it. And the next stadium didn't just survive pressure, it was shaped by it. Most stadiums are placed where the land is flat and the politics are easy. The Greater Bay Area Sports Center was placed where it would matter most, at the exact geographic intersection of Guangzhou, Shenzhen, and Hong Kong, serving a combined population of 86 million people within a 2-hour radius. That placement wasn't accidental. It was engineered into the brief before a single drawing was made. But the location was the easy part. The design challenge was brutal. Engineers had to deliver a world-class multi-venue complex in under 22 months, a timeline so compressed that every system had to be prefabricated, sequenced, and installed with zero margin for error. The facade curves weren't decorative. They were lifted directly from the hull geometry of Song Dynasty ships, translated into a structural skin that channels prevailing winds through the building's core, reducing internal temperatures passively. No mechanical cooling required for significant portions of the venue. And that passive cooling system isn't a gimmick. The curved roof profiles and ventilation channels were modeled across thousands of computational fluid dynamics simulations before a single panel was cut. The airflow was designed the way an aeronautical engineer designs a wing. 22 months. One of the most thermally complex stadium skins ever built, delivered on a schedule that most American projects wouldn't use just for permitting. But the next stadium didn't just manage air. It cleaned it. You've seen stadiums shaped like flowers before, but you've never seen one that actually functions like one. The Hangzhou Sports Park Stadium is modeled on a blooming lotus, and every petal of that roof is a structural decision, not a decorative one. The geometry distributes load across a radial steel network so efficiently that the entire roof uses 67% less steel than the bird's nest in Beijing. You heard that right. A roof covering the same scale of venue, built with roughly 1/3 of the material. But the engineering tension here isn't just about what was removed. It's about what the surface does. The facade panels are coated in photocatalytic titanium dioxide, a material that reacts with ultraviolet light to break down nitrogen oxides and airborne pollutants on contact. The stadium doesn't just sit in the city. It actively processes the air around it, functioning like a passive filtration system across its entire exterior surface area. The payoff is a building that does more with less, at every level. Less steel, less energy, less environmental debt, while performing at a higher standard than structures twice its material weight. That's not just efficient design. That's a rethinking of what a stadium is allowed to cost the planet. And the next stadium took that philosophy even further by hiding almost everything underground. Zaha Hadid didn't design a stadium in Hangzhou. She designed a landscape with a stadium inside it. From above, the Hangzhou International Sports Center reads as a smooth white disc, almost frictionless, almost featureless, but that surface is doing serious work. The horizontal shading slats wrapping the facade were modeled directly on the geometry of Longjing tea plantation terraces, and they're not aesthetic, they're solar control. Each slat angle was calculated to block direct solar radiation during peak hours while allowing diffused light to penetrate the interior without mechanical assistance. But the real engineering story is underground. What looks like a single floating disc from the outside conceals an entire buried podium, a full city of sports infrastructure pushed below grade to preserve the visual lightness of the form above. Aquatic centers, training halls, support facilities, and circulation systems are all stacked beneath the surface, invisible from street level. The structural challenge of burying that much program while keeping the disc above it appearing weightless required a foundation transfer system of extraordinary complexity, essentially a hidden structural city supporting a building that looks like it barely touches the ground. The result is a stadium that feels effortless from every angle, while concealing some of the most demanding structural engineering on the list. But if Hangzhou hid its complexity underground, the next stadium had no choice but to build on the most complicated ground imaginable. You know the old Kai Tak Airport in Hong Kong, the one where jumbo jets threaded between apartment buildings on final approach, close enough that passengers could see what people were watching on television. That runway is gone. But the ground it left behind is one of the most structurally hostile building sites in the world. Reclaimed land, marine sediment, and a water table that makes conventional foundation work nearly impossible. 800 seabed piles were driven into that ground to build Kai Tak Stadium. You heard that right. 800 individual piles, each one engineered to anchor into stable strata beneath layers of soft marine deposit. The foundation alone represents an engineering undertaking that most venues never approach. Then came the roof. Hong Kong sits in a direct typhoon corridor, and the cantilevered roof structure had to be designed to spacecraft-grade tolerances for wind uplift spanning the entire bowl without rear columns, which means every load transfers through a perimeter ring system engineered to flex and absorb rather than resist. Beneath the seating structure, the stadium sits on a triple-layered base isolation system designed to absorb typhoon-driven lateral forces without transmitting them through the building. A stadium built on 800 piles, under a cantilevered roof rated for typhoon forces, on land that used to be the South China Sea. But the next stadium didn't fight its environment. It turned sunlight itself into the structural spectacle. Most stadiums manage sunlight by blocking it. The Shenzhen Universiade Center was engineered to do the opposite, to fracture it, redirect it, and turn it into the defining visual experience of the building. The roof is a faceted triangular glazing system, thousands of individual panels set at calculated angles so that sunlight doesn't pass through uniformly. It refracts, it splits. Different sections of the interior are lit at different intensities throughout the day as the sun moves, and the exterior reads as a constantly shifting crystalline surface. But this wasn't achieved by simply cutting glass into triangles. The structural logic behind the faceted geometry required each panel to carry load differently depending on its position and angle in the overall surface. The engineering team had to resolve a roof where almost no two structural connections are identical. Every node, every joint, every transfer point is slightly different from the one next to it. At night, the building inverts entirely. The interior lighting turns the faceted skin into a glowing beacon visible across the bay. The same geometry that fractures sunlight by day becomes a lantern by night, without any additional lighting infrastructure. The structure itself is the light fixture. That's what happens when geometry and engineering are solved together instead of separately. And the next project didn't just wrap one stadium in an extraordinary skin. It wrapped an entire city of venues under a single one. Every stadium on this list has one primary architectural move. The spring cocoon has one move that covers everything. A single continuous PTFE membrane, a material more commonly associated with aerospace applications than public architecture, wraps a full-scale stadium, an arena, an aquatic center, and an office tower under one unbroken, wave-shaped skin. 4 completely different building programs, 4 completely different structural systems, unified under a single surface without a visible seam or transition. The structural challenge of that concept is almost irrational. Each building underneath has different column grids, different floor-to-floor heights, different lateral load requirements. The membrane above has to span between all of them without reflecting any of those differences on its exterior surface. The engineering solution involved a secondary steel diagrid suspended independently from the primary structures below, essentially a separate building built on top of 4 buildings, held together by geometry rather than by shared walls. The PTFE membrane itself is semi-translucent, meaning the entire complex glows from within at night, while remaining thermally efficient during the day. The material reflects solar radiation, reducing heat gain across all 4 venues simultaneously through a single envelope decision. 1 skin, 4 venues. One of the most complex structural envelopes ever built for a sports facility. And if the spring cocoon is about wrapping complexity in simplicity, the next stadium is about materials that shouldn't exist in a sports context, but do. Most building facades are passive. They sit there, they look like something, and they let weather happen to them. Longgang Stadium's facade is an active system built from aerospace-grade ETFE, pneumatic cushions, the same material used in the Eden project and in the panels of several major international airports, but pushed further here into a fully programmable luminous skin. Each cushion is individually inflated, structurally self-supporting, and capable of being backlit independently, turning the entire exterior into a pixel-resolution display surface that wraps a full stadium bowl. But the engineering tension inside is where things get genuinely extraordinary. The interior was designed from the ground up to reconfigure from a football layout to a full concert configuration in under 6 hours. That's not a crew swapping seats. That's a building system, retractable seating banks, modular floor sections, acoustic baffles integrated into the roof structure, all engineered to transform the venue's geometry without heavy machinery or extended downtime. The payoff is a stadium that earns its cost on non-match days, generating revenue as a concert and events venue while maintaining FIFA standard football configuration on demand. A building that changes its own shape in 6 hours, wrapped in a skin borrowed from aerospace. That's not stadium design, that's product engineering applied to architecture. And the next stadium borrowed its most critical technology from something moving at 200 miles per hour. Retractable roofs are not new. What's new is how Chengdu Fenghuangshan Stadium moves its. The roof panels don't run on conventional steel rail tracks with hydraulic drives. They run on magnetic levitation tracks, the same fundamental electromagnetic propulsion technology used in China's high-speed rail network, scaled and adapted to carry roof segments weighing hundreds of tons across a 5-span wide enough to cover a full football pitch. The engineering tension is this. A conventional retractable roof at this scale requires massive drive motors, constant lubrication, and mechanical tolerances that degrade over time. Magnetic levitation eliminates mechanical contact entirely. The roof floats above its track surface on an electromagnetic field, moves with almost no friction, and theoretically requires a fraction of the maintenance of any comparable system in the world. The entire stadium, not just the roof, but the full structure, including foundations, bowl, facade, and all operational systems, was completed in 34 months. For context, the renovation of Soldier Field in Chicago took over 3 years and involved far less structural complexity. 34 months for a stadium with a magnetically levitating roof. The technology exists, the timeline is real, and the next stadium didn't borrow from rail engineering, it borrowed from naval architecture. Dalian sits on the Yellow Sea coast, directly in the path of maritime typhoons, carrying wind loads that would compromise conventional stadium steel within decades. The engineering response at Dalian Suoyuan Stadium wasn't to build heavier, it was to build smarter. The structural steel throughout the entire venue is specified to naval-grade corrosion resistance standards, the same material classification used in commercial shipping and offshore platform construction, selected specifically because it was designed to survive saltwater atmospheric exposure for the full life cycle of the building. But the most extraordinary engineering decision at Dalian isn't in the structure, it's on top of it. A 1-mile continuous public ramp spirals around the exterior of the stadium in a double helix configuration, rising from ground level to the roof. 2 separate ramp paths interlock without ever crossing, one ascending, one descending, so that thousands of people can circulate simultaneously without conflict. The structural logic of integrating a mile of ramping circulation into the exterior skin of a stadium required the ramp itself to act as a secondary lateral bracing system, stiffening the facade against wind loads while carrying pedestrian traffic. A stadium that uses its public circulation as structural engineering. The next one generates its own power. Qingdao is a port city. The ground is complicated, the weather is maritime, and the brief was unforgiving build. A full-scale football stadium from an empty site in 3 years. The structural steel specified for Qingdao Youth Football Stadium is oil rig grade, the same classification used for fixed offshore drilling platforms in the North Sea. Chosen because the coastal atmosphere at Qingdao generates the same long-term corrosion risk as an open ocean environment. But the construction tension here is the timeline. 3 years from groundbreak to operational stadium, on a coastal site with marine foundation conditions, with a facade system that generates electricity. The photovoltaic panels integrated into the exterior skin aren't supplementary, they're designed as a primary power source, covering a significant portion of the stadium's operational energy demand through solar generation built directly into the building envelope. The drainage system is specified to airport runway standards, engineered to clear the pitch surface and surrounding infrastructure fast enough to resume play after the kind of intense rainfall events common to coastal Shandong. That's not typical stadium drainage. That's civil aviation infrastructure applied to a football venue. 3 years, oil rig steel, airport drainage, a self-powering facade, built from nothing. And the next stadium was built on ground that could move at any moment. Most of China's major cities sit in seismically active zones. Lanzhou sits in one of the most active corridors on the entire Eurasian plate, a region where the ground doesn't just shake, it shifts laterally in ways that can shear a building's foundation from its superstructure in seconds. The engineering response at the Lanzhou Olympic Sports Center wasn't to strengthen the building against seismic forces, it was to disconnect it from them entirely. The base isolation system installed beneath the 5 Golden Flowers complex is rated to the same performance standard used in nuclear power plant foundation engineering in China, a specification that requires the structure above to remain fully operational after a seismic event that would destroy conventionally founded buildings in the same location. The isolators are large-scale elastomeric bearing pads that allow the foundation to move independently of the superstructure, absorbing lateral displacement before it reaches the building above. 5 separate venues sit on this system simultaneously: stadium, arena, aquatic center, and supporting facilities, all isolated as a unified platform rather than individually, which required the transfer slab connecting all 5 programs to be engineered as a single seismic diaphragm of extraordinary scale. A sports complex engineered to survive what a nuclear facility cannot afford to fail. And the next stadium didn't sit on difficult ground, it was built into a cliff. Chongqing is a city built on mountains. There is almost no flat land, and the sites available for major construction are often the ones every other developer refused. Longsing Stadium was built on one of those sites, a hillside with a natural elevation drop of over 400 feet across the building footprint. That's not a slope. That's a cliff face, dressed as a construction site. The foundation engineering at Longsing is unlike anything else on this list. Because the ground drops 400 feet from one end of the stadium to the other, the pile depths on opposite sides of the building differ by factors that would normally make a unified structural system impossible. The engineering solution was an asymmetric foundation grid where pile lengths, load capacities, and transfer levels are individually calculated for every column position across the entire footprint, essentially a custom foundation design for each of the hundreds of individual structural supports in the building. The tension in construction was constant. Every pour, every lift, every piece of steelwork had to account for the differential settlement risk created by building a symmetric bowl on violently asymmetric ground. But the payoff is a stadium that reads as a natural extension of the mountain it sits on. Its asymmetric profile, matching the hillside so precisely that it looks inevitable rather than engineered. But if Longqing disappeared into a cliff, the next stadium disappeared into the earth entirely. Most stadiums announce themselves. You see them from miles away. The lights, the bowl, the steel rising above the roofline. Quzhou Stadium does the opposite. It disappears. The entire structure is semi-buried beneath a continuous, rolling landscape of grass-covered hillsides, pushed below grade so completely that you can walk across the roof without knowing there's a 50,000-seat stadium underneath your feet. From the surrounding parkland, it reads as a series of gentle green hills. Nothing more. But the engineering required to make a stadium invisible is anything but simple. Burying a structure of this scale means the roof has to carry soil loads, live pedestrian loads, and drainage loads simultaneously while spanning a full stadium bowl underneath a structural demand that required a heavy transfer roof system engineered to perform as both a building ceiling and a landscaped ground plane at the same time. The waterproofing system alone involved multiple redundant membrane layers, drainage composites, and root barrier systems typically reserved for underground transport infrastructure. Every detail was resolved twice, once for the building, once for the landscape sitting on top of it. The payoff is a stadium that costs the landscape nothing. It takes up space underground and gives the surface back to the public completely. A stadium you can hike over. And the next one didn't hide from the world. It changed what the world thought was possible. Everything on this list exists because of one building. Before the bird's nest, the idea that a stadium could be a structural argument, that the engineering itself could be the architecture, that the two things didn't need to be separate conversations didn't exist at this scale anywhere in the world. The 2008 Olympic Stadium in Beijing wasn't just a landmark. It was a permission slip for every single thing you've just watched China build. The structural system is a three-dimensional irregular steel lattice where no two members are identical. Not similar identical. 24 primary truss columns branch outward and upward into a web of secondary and tertiary steel so complex that the fabrication process required individual identification, cataloging, and precision sequencing of over 90,000 tons of structural steel components. The entire lattice was essentially a three-dimensional puzzle where every piece was custom-made and every connection was resolved from scratch. But here's where the construction becomes genuinely terrifying. The bird's nest only becomes structurally self-supporting once the full geometry of the lattice is closed, meaning the entire web of steel has to be held in position by temporary support towers during construction, because if you remove the supports before the geometry is complete, the structure moves. Every single weld sequence across a construction site the size of several city blocks had to be modeled, staged, and executed in a specific order. One mistake in sequencing didn't mean a delay. It meant the whole system was compromised. They pulled it off. And when those temporary towers came down and the lattice stood on its own for the first time, something shifted, not just in Beijing, but in what engineers and architects around the world believed was buildable. Every stadium on this list, the magnetically levitating roof in Chengdu, the buried landscape in Quzhou, the 800 seabed piles in Hong Kong, the aerospace skin in Shenzhen, every single one of them is a direct descendant of the moment that lattice stood up on its own. China didn't just build a stadium in 2008. It decided what the next 20 years of construction would look like. And then it built them all.